So what we need to do is we need to take our t differential equation, t dot over t is equal to minus alpha times k squared, and solve that ordinary differential equation for capital T. This differential equation is one that we know how to solve. In fact, we can solve it using the general techniques of first order differential equations. So one way we could do that is multiply by little dt on both sides and then integrate both sides. Solving that for capital T of t gives us capital T of t is equal to c e to the minus alpha k squared times t. If you don't see that step, there's a couple steps in between there. There's a natural log on the left-hand side, and then you have to take the exponential of both sides in order to get to this. It's worth working through those extra steps to make sure that you feel confident with that. We can actually go one step further for this solution for t of t, because we know that what the value of k is from our previous solution for capital X. And so plugging in k is equal to n pi over 2l for n odd, plugging that into the value of k in the exponential gives us a general solution for capital T of t that looks like this. There's a lot going on in the exponential there, but most of them are just constants. We have an n squared and we have a t. Okay, so now we've solved for capital X and capital T. So let's put this together and find the general solution. Take a moment to pause the video and see if you can write down the general solution from these solutions here. Okay, hopefully you paused the video and worked that out. Let's do that ourselves now. Let's first multiply our solutions for x and t to get the solution for u of x and t, where we multiply those two. And when we multiply them, we can combine the constants b and c into a new arbitrary constant, which I'll just call b twiddle here. And then I have my sine function and my exponential. The general solution is a sum of all sets of possible solutions like this for all n values that I'm allowed to choose. But remember, I'm only allowed to choose odd n values, so I have to restrict my sum to the odd n sums. But my general solution then looks like this. I'm just going to change that b twiddle into a b sub n, because in principle, each of these terms for different n's can have a different coefficient out in front. So we have now solved for the general solution to the 1D heat equation using separation of variables with these new sets of boundary conditions. It doesn't look all that different from what we had with both ends immersed in ice water, except now we have odd ends that we're using instead of all ends. So let's go back to our original question, which is to solve the 1D heat equation for these boundary conditions with the initial conditions that the temperature at T is equal to 0 is 3 sine of 5 pi over 2L times x. So we need to find the unknown coefficients, the b sub n's. So let's take our general solution and put T is equal to 0. Well, we put T equal to 0, we get e to the 0. That's just 1. We still have our b sub n's and our sines. And so in order for us to solve for this initial condition, we see that we must have b sub 5 is equal to 3, namely for n equal to 5. And b sub n is equal to 0 for any n that's not equal to 5. So our solution for all time is just picking up one term from that infinite sum of terms, the n is equal to 5 term. So we have 3 sine of 5 pi over 2L times x. And then in the exponential, we put n is equal to 5, so that n squared gives us the factor of 25 that's there. We still have alpha pi squared t, and then divide by 4L squared. So this gives us a solution for all time.